We are going to look at the box problem today and how it relates to higher degree polynomials. So here's the problem. Michael Scott at the Dunder Mifflin Paper Company has asked you to design a box that will hold the greatest amount, given a 50 by 70 centimeter piece of cardboard. The easiest way to make this box is to cut squares with edges of length x from each corner and fold the edges to form an open box. Okay, so let me draw a picture of what this would look like. Also, we should underline the important information. 50 by 70. Okay, so here is our piece of cardboard, 50 by 70. And from each corner, we're going to cut an X by X box. And then you would fold up these sides right here and make a box that didn't have a top. Okay, so it says sketch and label a two-dimensional diagram. There's our two-dimensional diagram. Remember, each of these are x's right here. Write the algebraic equation for the volume of the box based off your two-dimensional diagram. Okay, so here, if you remember from geometry, volume is length times width times height. Okay, let's write this equation. Volume equals, all right, our length right here is 70, but we're taking away two of the x's here. So 70 minus the 2x. Our width, likewise, is 50, but we're taking away two of these x's right here. So an x here and an x here. So that would be 50 minus the 2x. And our height, we would fold the box up, this x unit right here. There's our height as x. Okay, so there is an equation that represents the volume of the box. All right, find the zeros. Explain how they relate to the problem. Okay, so let's find the zeros. So here, one of our zeros is 0. One of our zeros, switch colors here. I used the darker purple. Okay. We want to know 70 minus 2x. What makes that equal 0? We will subtract 70 from each side. You get negative 2x equals negative 70. Divide by negative 2. So x equals 35. And our last one, change colors again, our last zero, 50 minus 2x. What makes that equal 0? Again, use algebra to solve. Minus 50 from each side. Negative 2x equals negative 50. Divide by negative 2. So our last zero is 25. How do they relate to the problem? Well, remember, x is what we cut. X is the length that we can cut from each side. So here are those x's right there. But how does that relate to the domain of the problem? Well, if you cut 25 centimeters from each side right here, 25 and 25, you're going to have nothing left, right? This would be 25. This would be 25. You would have nothing left. And likewise, on this one, if you cut 35 from each side, you would have nothing left. So this helps us find the domain of the problem. The maximum that we could cut from any side would be 25. We wouldn't have a box if we cut 25. Anything bigger than 25, so 35 obviously wouldn't work, but 25 wouldn't work as well. And if we cut 0 out, then we wouldn't be able to fold anything up. So this gives us the domain of the problem. So here, whatever we cut x has to be greater than 0, but less than 25. So again, this gives us our domain. We can't cut out 0, it won't fold up. We can't cut out 25, there'd be no sides left. And 35 is bigger than 25, that won't work anyway. So this gives us the domain. X, the corners that you cut can be any number between 0 and 25, and then you should be able to fold stuff up and make a box. Okay, multiply your factored form so it's in standard form. All right, so we had 3 terms here. I'm going to rewrite them. We had our 70 minus the 2x. We had our 50 minus the 2x, and we had our x. Last chapter we learned that when you're multiplying 3 things out, you take any two and multiply it first and take that answer and multiply it by the third. So I'm just going to distribute. I'll do 50x minus 2x squared. Let's multiply that by 70 minus 2x. It doesn't look nice. All right, so here it is. And let's make our box and get our numbers. Okay, so when we do that, we get 3,500x. 70 times negative 2x is negative 140x squared. 50x times negative 2x is negative 100x. Negative 2x squared times negative 2x is positive 4x to the third. So our volume in standard form, so it was in factored form, standard form would be 4x cubed, combine like terms. This should have been x squared. So negative 240x squared plus 3,500x. There's our volume in standard form. Let's graph this and see what it looks like. I had to change the window, so I played around with it, found a good window that worked. So I'm going to type it in on my graphing calculator. So I'll use the Scratchpad graph, but you can open a graph page and type in our function. Remember, you have to use x's instead of any other variable. So 4x to the third minus 240x squared, and then plus 3,500x. Oops, I said 3,500x. And if you graph it, we only see one of the zeros right here, which is at 0. So I changed my window. I went to Menu, Window, Zoom. You can zoom out. I just changed my window settings and played around with it. So here are the settings that I used. Let's see if I have it written down here. Okay. A minute there on my other sheet here. Okay, so I went from negative 10 to 10, no, to 50, because I know one of our zeros is 35, so I went up to 50. Minimum, I went to negative 5,000. Maximum, again, I played with this a lot to figure this out. I just wanted a good window to look at it. You could use Zoom Fit. Here's our graph. So again, we can see the zeros. We know that they're going to go through the zeros because the multiplicity is 1 on our equations. Let's look at that again. I'll show you what I mean. So here, the multiplicity is 1 for each of these zeros, so it's going to go through all the zeros. And let's sketch that graph below. So again, let's take a look at our graph. Okay, I'm going to try to sketch that. Let me maximize this. Okay. All right, here's our graph. We know at 0 it went through, at 25, and at 35. So it went something like this. Okay, so there's our graph. Here was 0, here was 25, here was 35. Using your graphing calculator, find the maximum point. Okay, so here was our maximum point. So let's use our graphing calculator and calculate the maximum point. We're going to go to Menu, Analyze Graph, Maximum. Go to the left and to the right. There's our maximum. Let's talk about what it means. 9.59, 1.5 e to the fourth. Okay, write it down. Talk about what it means. All right, so here's our maximum point. 9.59, I think it was. And then it was 1.5 e to the fourth. Okay, what does that mean? Well, x is 9.59, which is what we should cut from each side of the box. So this is what we should cut from the corners. And what does this mean right here? Well, this is the y value. This is like plugging in and solving. It's in scientific notation. So scientific notation, we have the 1.5 e to the fourth means move the decimal place over 4 times. 1, 2, oops. 1, 2, 3, 4. All right, so here it is. If we were to plug in 9.59 into the original volume function, so into this equation or the factored form equation, it would give us the maximum volume. The maximum volume is the y value, so our graph also gives it as 15,000. And this is centimeters cubed because it's volume. Okay, so there's an application. It gave us the maximum that we should cut from each corner and also the maximum volume with those corners cut at 9.59 centimeters. Let's review left hand and right hand behavior. So left hand behavior I'll do in blue. As it goes to the left, it's decreasing. And as we go to the right hand side, It's increasing because our volume would get bigger. But again, there were limitations, like the size of the paper, and that's why really, here's what we were looking at. And so if we talk about the left-hand and right-hand behavior of just this part of the function, it's decreasing. You hit your max, and it decreases from there. Okay, so there's an example of the box problem. You're going to try another application of this today in your assignment.